In this video, I'm going to present the results of my experiment about the motion of free-falling objects. For the experiment, I used a coffee capsule with a mass of 6 grams, which have been dropped from the rest. To calibrate tracker, I used a measuring tape with a length of 20 centimeters. I set the origin of the coordinate system to the center of the capsule, so it's moving on the negative y-axis. As you can see, the speed is increasing in the observed time interval of 0.434 seconds. For the first computer model, which simulates the motion of the object without drag, I set the mass of the object to 6 grams and the initial velocity to 0, because it is dropped from rest. I also set the initial position to 0, because the origin of the coordinate system is in the center of the capsule. For the calculation of the motion in the interval of 0.434 seconds, using Newton's second law, I calculated the weight force, which is the only force acting on the object in this computer model. It is acting in the negative y direction, so the negative j hat vector is necessary. Because this is the only force acting on the system, the net force is equal to the weight force. The rest of the loop is the code which is calculating the motion of the object through Newton's second law with the little time steps delta t equal to 0.001 seconds. Now I'm going to show you the computer model. As you can see, the graph looks similar to the one calculated by tracker. Next, I made a computer model for the motion of the free-falling object with drag. For that, I calculated the drag force, which was ought to be proportional to the square of the object's speed, which is the absolute value of the object's velocity. The drag force is also acting in the opposite direction of the motion, so it's acting in the positive y direction. That is why the j hat vector is used. Because now there are two forces acting on the system, the net force has to be the sum of the drag force and the weight force. The rest of the loop is equal to the loop of the previous program. I calculated the b in the drag force through running the program and optimizing b so the final position of the program is similar to the one of the experiment. It shows that b is very small. Now I'll show you the simulation of the program. I extracted the data from the tracker and the both computer models and plotted them in Google Spreadsheet. You can see the graph do fit in the observed time interval and the discrepancy is low. Furthermore, the graphs of the both computer models are equal because the value of b is so small. I think the reason for this result is that the observed time interval of 0.434 seconds is very small and the drag of the capsule is very small too. Looking at the velocity time graph, we can see that the velocity is increasing with the time, and there is no terminal velocity observed. The reason for this is that the drag of the capsule is so little that it doesn't have any effect on the motion of the object. With regard to the second question, would the terminal velocity increase if the object was thrown downward initially? I would say that the terminal velocity would stay the same, but the elapsed time until the terminal velocity is reached would be increased.